Hello, this is chapter 14 for the Top Hat Organic Chemistry textbook. With that, so where we're going to be talking about infrared spectroscopy as well as mass spectrometry. With that, so it's similar content. What's on the first edition of the book? They compressed some of the earlier chapters, so that the numbering is a little off from the first edition. So, but the content's still pretty similar. And that so. We talk more about spectroscopies. So a lot of what spectroscopy is, it's putting in light into your sample and seeing how it changes. You know what goes in, and how does your sample change the light. So we've already seen that when we were talking about chiral molecules and how they rotate plane polarized light. So this is a very similar sort of concept. But one of the things to remember is that with light, right, the shorter the wavelength, which is the distance between peak to peak for the wave, the shorter that is, the higher the energy. And so things like X-rays, right? That's they're very short wavelength, so they have a lot of energy, which is why when you go to the dentist, they take X-rays, they put a lead shirt on you. But for radio, something that has low energy, long the wavelengths, right? It's going to be low energy, which is why if you play the radio in your car, right? So with that, they send that out. It doesn't fry you, something like that. So what we're going to be talking about with this one is for infrared spectroscopy. So this is the fairly low, fairly long wavelengths, so lower energy. So in the not only the red part of the spectrum, but also going down to lower wavelengths. So we're really going to be working here for our sample. Now, the way this is going to work is you have to remember that the molecules in solution within the bonds, right? We've talked about rotation within the bonds, particularly with single bonds, but they can do more than that. They can rotate, but they can also wiggle and jiggle and stretch and rock and all sorts of crazy things. And each one of those has an energy associated with it. Okay, and so what we're going to do is we're going to be passing this IR light through the sample, and where it matches up, it's going to absorb. Okay, so we know we have our light source here, our infrared light source. So what we're going to do is we're going to send it through a known sample, so a reference sample, so we know exactly what light's coming out. And then we're also going to pass that same light through our sample, and we know, and so we're going to be looking at the differences for that. Okay, and where those, where the energy of the rotating or rocking or shaking or whatever you want to call it is similar to the energy of the photon that's passing through the sample. The molecule is going to absorb the light. So if you sort of think of a visual as if you're pushing your little niece or nephew on a swing, right? You can't just randomly push, or the swing won't go any higher. You have to get into the rhythm of it, right? So with that, in order to be able to get your niece to go higher and higher. And it's same thing here. If you put in energy at infrared light that's not at the same energy level as the wiggles, okay, it's just going to pass right through. Where they sync up, the molecule is going to absorb them. So it turns out that you can, there's some characteristic places where this, where the photon energies match up with the wiggles. Okay, and so we usually look at these wave numbers. Okay, down here. Oop. It's really just an inverse of the wavelength. Okay, and mostly it's just to make the numbers look good. But for wave numbers, okay, if you're below about 1400, those are going to be just regular old single bonds, whether it be carbon-carbon or oxygen or carbon-nitrogen or sulfur, carbon, chlorine, whatever. Between about 1500 and 2000, that's where we're going to start seeing all of the double bonds. Between about 2000 and 2500, that's where we start to see the triple bonds, whether it be alkynes or nitriles or whatever. And then above 2500, that's where we're going to start to see the absorption of the photons, where it's going to be between hydrogen and atoms. So you're talking about OH, NH, CH, various CH bonds, and we're going to be presented in different manners. Okay, but we usually think of this as wave numbers. Okay, and all wave numbers are is just the inverse of the wavelength. Okay, it just makes the numbers look a little bit better typically. Okay, and so what this is saying is that at these energy levels up here, so we're looking at how much light is getting transmitted. Okay, this is a relic of how they used to have to do these. And so typically for an IR spectrum, it's changing, but slowly. What we're going to do is we're going to say, okay, at these wave numbers here, nearly all the light is getting through. Okay, so we're looking at 90% of the light's getting through. But at this wavelength, it looks like it's absorbing a little bit of it. Okay, definitely at these wavelengths here. Okay, at these wave numbers, a lot of those photons are getting absorbed. Okay, so these are the sorts of things that we're interested in. When you're in this wavelength, photons of this wave number, nothing there to absorb them. But when we get down here to 1700, and what we're looking at is the number where that tip is. Okay, so in this case it ends up being 1717. Okay, at this one, at this wave, at these photons' energy, they are the molecule is absorbing that. And then you start to get into the sort of other sorts of ones. And so really, for the most part, you're just looking at a lot of the samples above about 14 to 1500. Those are more characteristics. You can narrow these down over here, but it's a pain in the neck. Right? So what you can do is you can come in here and you say, okay, the different types of bonds. So if you look at this molecule, okay, this C double bond O, okay, is very characteristic of that typically absorbs right around 1700, right? Because remember, in this region here, we're talking about double bonds. Okay, between 2000 and 2500, we're talking about triple bonds, and everything above here, this is atoms bonded to hydrogen. Okay, so OH, CH, and H, things like that. And so these are the double bonds. So this C double bond O will bond, that bond will absorb right around 1700. These guys here are in fact the CH bonds, okay, from these alkanes here. So what you typically get is you get these, you'll get these IR spectra. Okay, these IR tables, and what you're going to be looking at is you're going to say, like, so in this range here, it's somewhere in this range. There's a little wiggle room for where these are. So if you have just a regular alkane CH bond, its peak is going to be somewhere between 2850 and 2960. If you're looking at the CH coming off of an alkene, however, so the CH coming off the alkene, it's going to be a little bit higher wave number, a little bit above 3000. If it's coming off of benzene, it'll be 3030. If it's an alkyne, it'll be right around 3300. Okay, so you can sort of see, even though these are all CHs, how they're bonded to the surroundings will make a difference. Okay, if you're talking about OHs, they're typically in this 3200 to 3600, and it's usually a broad peak. So some of these will in fact overlap, and so we need to use other context clues to figure out, are we talking, if we have a peak at 3300, is it an alkyne CH or is it an OH? We don't know. We're going to have to look at other clues. Okay, So so if you have alkyne carbon-carbon triple bonds, right? So these are right where we'd expect them, between 2100 and 2200. Same with the nitriles, right? 2200 to 2220 to 2260. The double bonds, whether so the alkane, whether it's an alkene or it's a carbonyl, right? They're both going to absorb in that 1500 to 2000 wave numbers, but they're going to be slightly different. So the carbon-carbon double bonds are almost always down near 1600, while the carbon-carbon double bonds are typically nearer to 1700. And so you can get a little bit of information from that. And even then, it depends on what type of carbonyl you have. If it's a ketone, it's right around 1700, but if it's an ester, it may be closer to 1750. If you're an amide, though, it may be down in the 1600s. Okay, so you have to be careful. Just because it's C double bond O, you can actually get a little more information from that. But there are some definitely characteristic peaks. Okay? So the first one is the C double bond O peak, and so you can look at. So if you're on an exam, so I'm going to give an IR chart on the exam, but a lot of ones, whether you're talking about the ACS organic final or you're talking about the MCAT, they're not going to be, or DAT, they're not going to be giving you those spectros. So here's a few that will get you a long way. Okay, so the C double bond O peak. These are typically right around 1700. So if you see that, aha, I've got a double bond. Okay, and I probably have a C double bond O. So you can, you may not be able to tell if it's a ketone, an aldehyde, or an ester, or an amide, things like that. But you can definitely tell that it's right around 1700. So it's some sort of C double bond O. If it's down by 1600, it's probably going to be an alkene. Okay, so you can go ahead and narrow those down. Okay. Now you do have to be a little careful, because if you do have what's called conjugation, where you have a double bond adjacent to the C double bond O, not on it, but adjacent to it. So you have a double single double like this. That will actually push the signal down a little bit to a slightly lower wave number. So by about 30 or 40 wave numbers. So you have to be a little careful on that. They love throwing that sort of things on standardized tests. So just be careful. Another big ones are the OHs and NHs. Okay, because the OH, so they're all right around roughly 3000. Okay, but an OH peak is almost always going to be very, very big and very, very broad. Okay, it's going to be something big and honking like this, which is bad because for a sample, because if you have water in your sample, so if you're in the lab and you're running this, the sample needs to be dry, or else you're going to just get this massive water peak. It doesn't matter what OH is going to be, whether it's on your sample or in the water, it's still going to give you this one right here. Okay. So notice how, if you're looking at cyclohexanol here, notice how there's no peaks right around 17, no 1700 peak, no 1600 peak, nothing in the triple bond range. Okay, but we do have this OH peak. These guys here, right? Those are the alkane CH peaks. Those are always there. Okay, and NH peak is going to be still going to be in that exact same range. However, it's rarely going to be this broad thing, and even so, it's going to be it's going to be more like a quote unquote normal peak. Okay, it's going to be shaped. It's not going to be quite as broad as that. So if you look at the peak strength, okay, you're not going to see that. Okay. Now you can look at substitution patterns. So there are ways of doing this. So you have to, so a monosubstituted, so if you had just like chlorobenzene, okay, you would have the CH peaks would be, you would get 2 of these peaks. If you have orthosubstituted, which is 1, 2 on the benzene, the CH peaks you would only give this 1. If they're meta substituted, so you had 1, 3 dichlorobenzene or something like that, you would get these 2 peaks. And if you were para substitute, so 1, 4, that cross from each other, you would get this single peak. And so you can look at, but I'm not going to test on this because we haven't really talked about orthometapara, but it's one of those things where you'd want to, you may want to keep an eye on those. Okay, some of them are 2, some of them are 1. Now, so how are you going to, so what IR is really good at, okay, is telling you what functional groups are present within the molecule. It's also really good at telling you what functional groups are not there, okay, because what is there and what's not there, okay, are both equally important. Okay, so if you're looking at this molecule here, so you have two samples. You don't know what, the bottle has fallen off, but you're pretty sure that it's based on the formula. It's going to be one of these two. Okay, you just don't know what. So you take an IR spectrum of it. Okay, and out comes 2950 and 2150. Okay, those are the 2 peaks. And so you come down here. So you say 2950. Okay, so what could that be? So it could be, it could be. Well, this is in red. So, so if you're looking at this 2950, okay, what could be in here? Well, it could be this, right? It could be this. Yeah, so that's like what it could be. But notice how we can't have a carboxylic acid. It can't be this, right? Because we don't have a carboxylic acid as one of our possibilities, right? So we can go ahead and eliminate this. So most likely that 2950 is just going to be an alkane CH. Okay. Now the question is, what about the 2150? Well, we come down here, and so it could be this, and it could be here. I think that's 2150. Okay, I think that's about it. Yep. So you've got the alkyne peak, and that's it. Okay, well that makes sense because it's a little bit below what the range of the nitrile, but that 2000 or 2500 is a triple bond. Okay, so this is a C triple bond. C. Okay, so that makes sense because both of them have a triple bond in there. So the question is, which one is it? Okay. So what we would need to do is we would need to look at what's not there. Okay, and if you look at the molecule, right? So this is CH3, CH2, CH2, C, and then CH. Okay. If you look at this one, so CH3, CH2, C, C, CH3. So this one has 2 CH3 groups, okay, but that's not really going to tell you anything because those are more like alkane peaks. But the big difference, okay, is this right here. Okay. If our sample was this, we would need a peak at 3300 as well. So if you were to take this as a pure sample, what we would get is we would get the 2950, we get the 2150, and we'd also get a 3300 peak because that one is right there. We would also get a peak of a CH hanging off of an alkyne. We don't have that in our spectra. So it can't be this one. It can't be this green one because if it did, we would need to have that 3300 peak. Our sample doesn't have that. And so that means if it can't be this one because this peak isn't present, then it must be this one here. Okay, so the fact that there is this 3300 peak missing means that we can't have the triple bond at the end of the molecule because if we did, we'd have a 3300 peak. We don't have that, so it has to be this because it can't be this. So it has to be this. Now we can use IR, okay, to monitor reactions. Okay, so if we look at a reaction and we look at it after we've added the starting material, it should be all of this, right? We're going to put this in. We're going to put some catalyst in, some some phosphoric acid. Okay, we're going to get the CO. We're going to get a CO bond. We're going to get an OH bond, right? And we're going to see our CHs and CCs. No big deal. As the reaction goes forward, okay, we're going to be consuming this. So the concentration of this particular product is going to be decreasing, which means the peaks associated with those are also going to decrease. As we make more and more of this, okay, the carbon-carbon bond here, the carbon-carbon double bond, okay, the carbon-carbon double bond and the CH bond that's coming off of the alkene, those are going to start to get larger and larger, because as we build up the concentration of this, okay, we're going to get more and more of that, so it's going to absorb those wavelengths more. Okay. Now you can't monitor the OH, right? Because you say like, well, yeah, right, we're losing that OH. The problem is it's turning into water, right? Because remember, water is just HOH. So the water here is going to absorb pretty much the same as the water or the OH bond over here, or the OH bond over here, and the OH bond and the water are going to absorb pretty similarly. So you're not going to be able to tell that difference. Okay, but we are going to be losing the CO bond here because that's not present over here, and we're also going to be gaining the alkene peaks, both the carbon-carbon and the carbon and the CH. Okay, so you can look at this over time, okay, to see how the reaction is going. Okay, next up is mass spectrometry. So this is notice how I didn't say spectroscopy, right? So for this one, we're going to be actually measuring the mass, okay? And so we use this to get the molecular formula for this. So how, what's the overall mass of the molecule? And from that, we can infer what the formula is, okay? And so one of the things that has to happen is we need to get our sample, whether it's in the liquid phase or a solid phase, we need to get that up into the gas phase, so we can analyze that. Okay, so we can get it moving along a stream of air, or of gas, I should say. What we need to do next is that having the molecule there doesn't really do us a whole lot of good. What we really need to do is we need to give it a charge. Okay, and so the way this works, and so what we do is we send it through a beam of electrons, right? So it would be like the sending you through a waterfall, right? So it's going to be coming down, and you're going to get wet as it goes over here. What happens here, however, is let's say you've got, I don't know, let's say you've got this molecule here. What's going to happen is you're going to take an electron, right? And you're going to bombard the molecule with it. And so, right, so each one of these, each bond, remember, is going to be 2 electrons. But if you've ever tried to put 2 north magnets away, if you have a magnet here and you try to put a north, right, it's going to scoot it away. That's what happens here. When you put in an electron from this beam, what's going to happen is it's going to deflect away one of these let me put this in dang it. What's going to happen is one of these electrons is going to get deflected away. And so what you're going to end up having is you're going to get a molecule, right? Because we've lost an electron. Okay, so we're down an electron. Okay, and so the molecule itself is going to have an overall charge of +1. Okay, so but the problem is now we're only holding these 2 bonds together as a with 1 electron instead of the normal 2. Okay? But that's fine. Okay, so we inject our sample into here, and we accelerate it. Okay, we get it up into the gas phase, so we heat it. We vaporize the sample with heat. Right, we get it above its boiling point, so get it up into the gas phase. stuff like that, and we accelerate it. Accelerate it going through a hole, right, stuff like that. So, and we send it through this beam of electrons. That's going to, so if we have a negative charge here, right, our sample is going to get attracted to that negative, right? Anything that's positively charged is going to get pulled towards this negative charge. That sends it through. So this is an accelerator plate, and that speeds the sample up. And what we're going to do is we're going to put it between two magnets, and what that does is it deflects it. Okay, and if you're really lightweight, so you're like a little go-kart, right? You can take this turn really sharp. Okay, and so your path will be over here. So this is the go-kart. Okay, but if you're really heavy, okay, you're not going to be able to take that. You're not going to be able to take that corner very fast, and so you're going to come out here. So if this was, say, a semi-truck, you're not going to be able to make that corner, right? Because you've seen a semi-truck take a corner quickly, they got to swing way out wide. Okay, so by making it go around this corner, what you can do is you can separate out the fragments by size. And so what you can do is you can say you can put a detector here, 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 here. You can put a bunch of these detectors in here, and you can tell where these positively charged fragments or molecules are striking it. Okay, and you can count them up. Okay, and so what you get is so you're able to deflect these, and that deflection causes the molecules to separate out by size. Right, the little things, the low mass things deflect a lot. The big heavy things don't. Okay, and so what ends up happening is you just get a count of. So at 15, we've got a few. At 15 mass, we've got a few of them coming here. But if you're looking at, say, the detector that detects 29 molecular weight, okay, we're going to have a lot more strikes on that detector. At the 30, we get just a little tiny bit, but we haven't seen no strikes at any of these sizes. Okay, I can this up, right? But right around 40. Right, so for that we get a little bit. 41 we get a whole bunch. 42, a moderate amount. 43 we're going to get a whole lot of samples hitting at the detector that's detecting 43 molecular weight. Okay, and then we get a lot, particularly a lot at 57. Okay, that's the highest. So we're going to just set that at 100, at 100%. So this is the highest. So we're going to set it relative to whatever the highest is, and that's what's called the base peak. That's the one where we set it to 100%. Okay, base peak isn't necessarily particularly important. Okay, what really is important is this guy here, the heaviest the heaviest molecule or signal that we get out. That's what's called the parent ion. Okay, now we'll talk about that little tiny thing that's right above it in just a second. But this right here, this is the mass of your signal. Okay, this is the mass of your sample, I should say. Okay, that's the important one. Okay, not the base peak here. Okay. The problem is, okay, so if our sample is 86, what the heck is all this other stuff? It's not, even if you had a pure sample, you'd still get all this other crazy crap in here. Okay, what's happening is as the molecule is traveling from that electron beam to the detector, okay, it's going to fragment, right? Because remember, there's only one electron holding that bond together, okay, and that's not particularly stable. So in the time it takes to get down there, it will have fallen apart. Okay, a tiny bit of a tiny bit, okay, is all we need for it to arrive intact for us to get the the parent ion. Okay, but these are all the fragmented samples. Okay. And rarely is the base peak going to be the parent ion. Very rarely is it ever. Okay, but we really only care about the parent ion because that's what our mass is going to be based on. Now, remember we're sending it through a beam of beam of electrons, right? So you can knock this one out, or in a different molecule it could get this one knocked out, or this one knocked out, or this one, or this one. And when that happens, you get a positively charged fragment, and then this you get a one electron bond that can then break. Okay, and so so how these things are breaking is how we get a 71 or a 57 or a 43. Okay, so we're just going to be looking at the positively charged one. The book goes into great detail for how you can look at the fragmentation. I don't like doing that. I think that's more for an analytical chemistry class. But know that it can. Okay, because really all we want to do is we want to get that parent ion. So if you look at here, if you look at the base peak, right, that's always just the highest, right? So that's going to be here. So this is the base peak here. Okay, the parent ion is going to be the one that's heaviest, and you're going to want, in this group, you're going to want the tallest of this heavy peak, and so this is the parent ion. This is the one we really want right there. Okay, so this molecule, right? So this is 100, right? So this is 110, so this would be 105. So ours is, say, 106. Here, this one is what? So that's 90. So this would be, the base peak would be at 91. Okay. But it's really the parent ion that we're interested in. So, okay. Now, those little peaks that were on either side of this, right? So that these little peaks down here, okay, what those are isotope peaks. Okay, so for carbon, nearly 99% of it is going to be carbon-12. Okay, but 1% of those, unless you purposefully want to put in only carbon-12s or only carbon-13s, okay, just naturally 1% of your sample is going to be carbon-13. Okay, so if you have hydrogens in there, you're going to have a little bit of deuterium in there. If you have say an oxygen, you're going to have just a teeny tiny bit of oxygen 17 and a little bit more of oxygen 18. Okay, so what's going to happen is, if your molecule is 106, what can happen is you're going to have a very tiny amount of a very tiny bit that's your same molecule, but it just so happens to have either a deuterium or a carbon-13 within it, and so it's going to have one extra mass, right? Because it has one extra neutron within it. Okay, but it's going to be a very tiny amount. Okay, and so if you look at this proportion, you can actually use that to calculate, because you know for every 1% it's going to be a carbon-13, so you can figure out. You can get some information on there, but for the most part, it's not going to. There's not always a lot of information, but that's what those extra little heavier peaks are. It's the different isotopes that are showing up, that small percentage. Now there are a couple ones that are very diagnostic, and in particular the chlorine and bromine. Okay, so in a normal chlorine sample, 3/4 of your sample is going to of the chlorine atoms are going to be chlorine-35, but 1/4 of them is going to be chlorine-37. So what's going to happen is you're going to have 1/4 of your sample is going to have a chlorine in there that has 2 extra neutrons in it. Okay, so you're going to have quite a bit of what would normally be your parent ion with 2 extra masses on it. So it'd be an M+2. Bromine is great because here there's almost no difference, right? It's 50-50 on 79 or 81, and so you're going to get half of your sample, right, with bromine 79, and the other half of the bromines in those atoms are going to be 81, and so that's really diagnostic. Okay, so what's going to happen is if you have 2 peaks where the M and the M+2 are 2 away from each other, like this, that's really diagnostic of having a bromine in there in your molecule. So because you have this isotope peak that's way large. Okay? And if you have one that's roughly 3 to 1, right? So 75% of is regular chlorine, while a quarter of it has 2 extra neutrons in it. So having this roughly 3 to 1 peak in here is very diagnostic of chlorine. Now the other quirky thing about mass spectrometry is what's called the nitrogen rule. So an odd number of nitrogens, as it turns out, will result in an odd value. Other ones are actually going to be just even. Okay, so if you look at something like methane here, okay, its value, its mass is going to be 16. But if we put in a single nitrogen, okay, notice how it goes to an odd value. Okay? Now, if we have 2 of them, right? Remember, if you add an odd and an odd, right, you get an even. So it goes back to even. So what ends up happening is, so if you have an odd number of nitrogens, you're going to have an odd mass. Okay. So this is really the only regular one where you get these odd numbers here. Otherwise, your mass will be your parent ion is going to be even. Fragments are, things go out the window with that. But for the parent ion, okay, if you have if your M plus is odd, that means you probably have a nitrogen in there. It means you have a nitrogen in there. Okay, so how are we going to solve these? Okay, so usually there's a couple of different ways that you can do this. So I have a slightly different approach for this. Okay, you're not going to be able to get everything you need. So for that, there may be still some ambiguity, and we'll talk about how we can narrow it down to a single structure when we talk about NMR. About that in the next chapter. But for this one, we can really narrow it down. And so one of the ways we can do is we can look at how much unsaturation there are. And so if we do the degree of unsaturation calculation, right, we can figure out how many pi bonds or rings are in there. Okay. Now we don't necessarily know how many there are, but but we know when there's none, or if maybe there's some other context clues to figure out what it could be. Okay, and notice how there's not in this equation. Notice how there's not oxygen, right? Don't put that in your calculation. Okay, it's not part of the formula. You just ignore it. Okay, for calculating the DOU. Okay. Now the other thing you can look at is to figure out how many what's the maximum number of hydrogens that I can have on a molecule for if the hydrocarbon was completely saturated. Okay, if we didn't have any DOUs, right, any rings, any pi bonds or anything else like that, what's the maximum number of hydrogens we can cram onto there? And it turns out that there's a formula. So for every n number of carbons, the maximum number of hydrogens we can get is 2n plus 2. Okay? And if you notice, if you look closely, that's the 2n plus 2 is right there. That's where that comes into. That's where that plus 2 in that formula comes into play. Okay, so if we have 4 carbons, what's the maximum number of hydrogens we can have? Well, it would be 2 times 4, right, plus 2. So that would be 10. Right? So a fully saturated hydrocarbon with 4 carbons, the maximum number of hydrogens we can have is 10. If we look down here, right, if we have 10 carbons plus 2, right, the maximum number of hydrogens we can have is 22. Okay. So how is that going to help us? Okay, so if you have something, so propose a valid structure for the hydrocarbon with an M plus of 32. Okay, so what we can do is we can say, okay, well, it's a hydrocarbon, right? So that just means that we have some number of carbons and some number of hydrogens. We don't have another sort of, we don't have any nitrogens, we don't have any oxygens or sulfurs or chlorines or anything else like that. Okay. So what we want to do is to come in here and try to figure that out. Okay, so let's say we had a hydrocarbon that had, I'm sorry, so 8 carbons. Okay. Well, the max number of hydrogens that we would have, okay, max number of hydrogens would be, right, would be 2 times 8 plus 2, right? So, so this way, 16, was it 18? So if we had C8, the maximum number of hydrogens we can have is 18. Okay. Now, if we had this, right, what would be its mass? Well, okay. So if we're looking for the mass of C8H18, right, so we have 8 carbons. Each one of those is worth 12. So if you look at the periodic table, right, the larger number is on the periodic table. That represents the molar mass, right? So each one of those carbons is worth 12, right? So we have 8 of them, right? We also have 18 hydrogens. Each one of those has a mass of 1. Okay, so I think that's what, 96. That's going to be 96 plus 18, right? So that's what, 114. Okay, so the maximum mass of an 8 carbon hydrocarbon would be 114. We can't shove any more hydrogens in there. Okay, so let's add another carbon, right? So what if we had 9 carbons? Well, in that case, the max number of hydrogens would be, right, 2 times 9 plus 2. So that would be what, 20? Okay. So that would mean if we had a 9 carbon hydrocarbon, right, so it would be C9H20. So if we run the calculation, right, so there's 9 carbons in here, right? Each one of those is worth 12. And then we also have 20 hydrogens, right? So that one's 1. Okay, so that's what, 108, right? Plus 20. Aha. That would be, what is it? 128. We are so close here. Okay. But there's no way that we can pack in 4 extra hydrogens to get up to 132. There's just no place to put them. So what we need to do is let's go up to 1 additional carbon, right? So now we're at 10 carbons, right? So what's the maximum number of hydrogens we can have, right? Well, that's 2 times 10, right, plus 2. So that would be 22, right? So that means for C10H22, that would be a fully saturated hydrocarbon with 10 carbons. Okay, so we have 10 carbons, each one of those is worth 12, plus 22 hydrogens, each one of those worth 1, right? So this is what, 120 plus 22, right? Aha, 142. Now, what does this give us? This allows us, because this is the maximum number of maximum weight that we can get for a particular for a 10 carbon hydrocarbon. To get to 132, all we would need to do is we would need to subtract. If we want to get to 132, what we can do is we can subtract 10 hydrogens from that. Okay, so C10H12. We can't subtract a carbon, because if we did, then we'd only have 9 carbons, and then the maximum we could have is 128. So what we want to do is we want to get just past what the mass would be of what we're looking for, and then we were going to reduce the number of hydrogens, right? Because remember, this is just the maximum number of hydrogens we can have. We can have fewer, that's fine. So if we take away 10 10 hydrogens, we can get to that 132, right? So 10 plus, right? We have 10 carbons, each one of those is worth 12, but now we have 12 hydrogens, each one of those is worth 1. Okay, and so that mass is 120 plus 12, which would be 132. So that is our mass. That's what our formula would be. Okay. So this is a big step, right? We know what the formula is, but that's not actually what I'm asking for. I'm asking for propose a valid structure. So the easiest thing to do with that is to just run a DOU calculation, right? So it's 2 times the number of carbons, which is 10, plus 2. We don't have any nitrogens, right, or halides, but we do have 12 hydrogens, right? So if we run that, so this is what, 22, so it ends up being 22 minus 12, ends up being 5. Now a good rule of thumb is that if it's 4 or higher, you probably have a benzene. Okay, so we have 10 carbons to work with, so we could do something like this. That's six of the carbons. So now we need another 4. Okay, so we could do 1, 2, 3, 4, right? 1, 2, 3, 4, and then put, say, a double bond here. That's fine, right? We've got one ring and 4 pi bonds. We could do, right? We could do this. Right? 1, 2, 3, 4. Right? We don't have to do a benzene, but this one, if you calculate all of it, okay, that's a really terrible double bond there. So we could have a benzene and a ring or something like that. You don't have to have a benzene. We just have to have a hydrocarbon with that formula. Okay, and so what we can get is we can get acids. So that's what we're doing here. So you could get, say, 2 rings and 3 pi bonds. You could get 4 rings and 1 pi bond. You could get 1 ring and 4 pi bonds. So these will be all valid structures because we don't have any more information about that. But the big thing is we can find this formula here, okay? And you can, try to propose. So if you combine this with IR, you combine it with the NMR, which we'll talk about in the next chapter, you can go a long way to figuring out which one of these structures it is. Now the other way that we can do this is if we have, say, a valid structure here, and but we include some sort of functional group. So for here, so it's 86, okay, but it has an alcohol group, okay. So what's going to happen is, so we're going to have some number of carbons and some number of hydrogens, but since it's just a single alcohol group, we know that it's going to be, we're going to have an oxygen in there too. So that formula is going to equal 86, right? Now, one of the things is that we know what the oxygen's mass is going to be, right? So it's going to be some number of carbons, some number of hydrogens, plus 16 is going to be 86. So that means that the hydrocarbon part of this is going to be equal to 70. Okay, so now when we're trying to look at this, we're not targeting the 86, we're targeting the 72, because we already know that 16 of that is going to be the mass of the oxygen atom. Okay, so the total number of carbons and the total number of hydrogens is going to equal 70. And you would say, like, wait, aren't we going to subtract out the OH? No, that's included in this hydrogen. We have to remember that it's there, but we're just going to talk about the total number of hydrogens. So if we're looking at this and we're going to say, okay, so let's say, so we're targeting 70 here, and so let's say we have four carbons, right? So the maximum number of hydrogens is going to be what? 2 times 4 plus 2, right? So that's what, 10? So this part here would be C4H10, right? So 4 carbons, right? Each of those was worth 12, plus the 10 hydrogens. Each one of those is worth 1. So what we can do, so 48 plus, right? So it's 48 plus 10, right? So we're going to be at, what's it, 58. Not quite there, almost, but not quite. So let's try 5 carbons. So here the maximum number of hydrogens, right, would be 2 times 5 plus 2. So that's 12. So that must mean this formula would be C5H12. By the way, that's supposed to be it's a really bad 4 up there. Which would give us 5 times 12 plus, right, we have 5 carbons, each one of those is worth 12 molecular mass, and then we have 12 hydrogens, which would be 1. So this would be, what, 60 plus 12, right? Aha, 72. So how do we get, right, so this is what the maximum, the hydrocarbon part could be, but if we were to put an oxygen on here, it would be 88. Okay, so what we need to do is we need to reduce the number of hydrogens by 2, right, so that it's C5H10, right, and then we're going to add, so that is the hydrocarbon piece, and so the final formula is going to be C5H10O. So this part is going to be worth 70, and this part is going to be worth 16. Right? So 5 times 12, right? That's 60, and then we're going to get another 10 from here, right? Because each one of those hydrogens are worth 1. So if this part here is going to be worth 70, this part is going to be worth 16. So all of that is going to equal our 86. So now we need to do a structure. Oops. Okay, so we're going to look at here. We're going to come in here. We're going to say, okay, so DOU, 2 times the number of carbons, so C5. So this is our formula here. C5H10O, so 5 plus 2. We don't have any nitrogens. We don't have any halides. But we do have these 10 hydrogens. So 2. So it ends up being 2 over 2, which is 1. So we have some sort of DOU. Okay. So we could do, say, so if we have 5 carbons, we could just do that, or say OH, methyl. We can have a, right? Or we could do, say, I don't know, this. Right? We could do a pi bond, just as long as it has an alcohol in it, right? And it has this number, it has that formula, and it has an alcohol group in there. It's good. So it could be, any of these guys. Okay. Now, one of the things that you can do with mass spectrometry is attach this to a separation technology. And so for here, this is the classic one is gas chromatography. And so if you have a mixture in your sample, so if you have several different molecules in there, what you can do is you can then separate them out through chromatography. And so they're all going to be running, as they run through these coils, they're going to be running at different speeds. Okay, and so they're going to emerge out of the chromatography one at a time. Okay, one of the molecules is going to run a little slower than the other, so you can separate them out. So as it's coming out, then it gets injected automatically. It goes directly into the mass spectrometry. So we know that the sample at this, we can separate the samples out and then get their individual masses. Okay, so this sample here for THC, okay, so this is the reason why this was developed was actually for the military to do drug testing. Okay, and so if we look at THC, so if we analyze, so each one of these each one of these compounds that comes off gets run into the mass spectrometer. And so if we look at, we can separate the THC from the CBN from here. Okay, each one of these can go individually into the mass specs. So if we take this part of the spectrum and run it in the mass spec, we get a fingerprint. Here, let me do this. Okay, we get a fingerprint region. Okay, so how it fragments out is distinct. Okay, and so what they do is they know what compounds they're looking for, and so they look for it's literally called a fingerprint, a fragmentation fingerprint. And so that's how they can tell if you have THC in your system or cocaine or methamphetamine or whatever. It's because they're looking at, they can separate out all the different compounds that are in the urine and separate them out so that they can look at them, analyze them individually, and then they take they get a mass spectrum of each one of those compounds individually, and they're looking at how it fragments. And so THC fragments in this particular way. Okay, and all of this is automated, so a computer can say, oh, it can flag it. This sample here, had a, had some partying, the other day. So because it has THC in the system. Okay. Now, one of the things is that we talk about fragmentation, and that has that can be important, but there are other ways of getting a charge on your molecule. Okay, and the big one, the two we're going to talk about, the first one is electrospray. Okay, what this does is this MALDI. Okay, what this does is instead of adding knocking out an electron, okay, to allow it to fragment, what we're going to do is we're going to add an H+ into the molecule. Okay, if we add an H+, then we're going to automatically give it a plus charge, obviously. But we also have to take into account the fact that now it has one additional mass. Okay, so if your sample would normally have 250, molecular weight, the signal that's going to be coming out is 251 because it's your signal plus that H+. Okay, plus the extra hydrogen that's on there. The nice thing about this is that it does not cause your your sample not to fragment. So you're automatically going to be getting out that parent ion. Okay, you don't have to worry about it fragmenting. It can also do much larger samples, or samples that are much larger. Okay, so in this case, 100 Dalton. If you're a biologist, or it's just grams per mole. So the problem is getting in the gas phase, and so for things that large, what we have to do is we have to use what's called matrix-assisted laser desorption ionization to get it up here. And literally, what you do is you have a gold plate. You mix your compound with this matricing, with this extra compound, and you dry it on the sample, and then you literally fire a laser at it. Just like a video game, right? You sort of get the target on there and fire away. Okay, when the laser hits it, it's gonna literally blast the sample up into the gas phase, and because it has this matricing part in there, it gets this positive charge, and so now your molecule is up into the gas phase with a positive charge, and that can go into your mass analyzer, something like that. But by doing this way, we can do very large samples without needing to, without the fragmentation. This is a great way of doing it. And lasers make everything better. So okay, and I think that's it. So good luck.